Hey everybody, it's Mr. Carr again. Today we're going to be looking at 8-1 day one. We're going to be looking at our introduction to vectors. Okay, they're related to some of the trigonometry problems you've done with triangles. We're going to change things up a little bit when we talk about what vectors are. So let's get right into that. A vector, let me start with that. It's a quantity that has both a magnitude and a direction. Okay, so when I talk about that, when I say a magnitude, sorry, you know what? Let's go back to scalar real quick. A scalar is a single real number that describes a physical quantity, such as a speed or weight. This number indicates the size of the quantity. So in this case, we're going to use it in terms of what's called a magnitude. So a scalar is anything that you can associate like a number to. So like it's like saying it's weight. Something weighs exactly 100 pounds. That's a scalar. Okay, we can talk about it in that same something if it grows by a factor of 4. That's a scalar. It has a scalar value of 4. So a vector is a quantity that has both a magnitude and a direction. So the direction we want to say like how far is it going, as well as like what kind of with the magnitude, like how far does it go in a certain direction, especially in X and Y. So let's take a look at this. State whether hockey puck shot northwest at 60 miles per hour is a vector quantity or a scalar quantity. Okay, so the idea here is that if I talk about something, it's being shot at northwest. Okay, so it's doing something like this. So it's doing that at 60 miles per hour. Okay, this quantity has a magnitude of 60. That's what we're trying to say here. The direction is going like this way right here. Oh, shot northwest. My bad. I put that in the wrong spot. Should put that up here. Okay, so it's shooting northwest that way at 60 miles per hour. So it goes in that direction. Okay, but the magnitude is 60. So that makes it a vector. Let's see here. So this is going to be a vector quantity because it's made up both of magnitude and the direction. Sorry, I misunderstood the question there. So this distance is what's giving us the idea of a vector. If we say something that has a magnitude that is 60 miles per hour in this case, and it has to have the direction. If I just say that the hockey puck was shot at 60 miles per hour, that's just a scalar. There's no direction there. So that does not make it a vector. That's the difference. State whether a tennis ball served at 110 miles per hour is a vector quantity or a scalar. Okay, I just talked about this. So we say it's 110 miles per hour, but we don't give it any kind of direction to it. So that means that my magnitude is just 110 miles per hour, making it just a scalar then in that case. Okay. Draw an arrow diagram for V is equal to 10 newtons at force of 30 degrees to the horizontal. Okay. So the idea here is talk about an arrow from here. So 10 newtons at 30 degrees to the horizontal. So basically, I'm going to draw it so it's right here. This is 30 degrees, and then this is going to be V is equal to 10 newtons here. So that's what we're looking at there. So if it's 30 degrees to the horizontal, from the horizontal line, it makes 30 degrees going up like that. Okay. Represent a vector geometrically here. So draw an arrow diagram for Z is equal to 25 meters per second at a bearing of S 70 degrees west. This is what's known as a quadrant bearing. This, if I read it out loud, it's going to be 70 degrees west of south. Okay, so that's how we treat it. So the idea is that if we start from the southern direction, then we want to move 70 degrees west. So if I look at this here, since this is my southern direction, let me do this right here. So from this spot right here, this is my southern direction. I'm going to go 70 degrees this way. And then I draw this out here as my actual bearing. And that's going to be 25 meters per second is the idea. So velocity here is 25 meters per second. Okay, so that's how we're showing this in terms of direction and magnitude. Okay, with our velocity as well as the direction it's going. So we want to draw an arrow diagram for t equals 10 miles per hour at a bearing of bearing of 0.25. This is what's known as a true bearing. A true bearing is always clockwise from due north here. So from here, from north, we're going to go clockwise. So it's going to move that direction. So because even though it's 3 digits, it's 0.25, we're just moving 25 degrees from north. So I'm going to do this right here. Okay, sorry about that. Yeah, so we're going to go from this scenario here. We have 25 degrees, basically 0 to 5 is just referring to 25 degrees. So we're going to go for 25 degrees from north in a clockwise direction. And that is going at 10 miles per hour. So that's going to be right here, just like this, at t is equal to 10 miles per hour now. Okay, so the other part of our vectors, the idea here, we talk a little bit about this, our triangle method. To find the resultant, the resultant of A and B. So it's kind of like a combination of the two, like what happens when we add them together. So we translate B so that the tip of, so if we look at it like doing two different directions, like we're going to move on vector A this path and then vector B. The resultant is almost like saying if we take the two vectors and put them together, then I am going to draw a straight line between these two, and that's going to represent A plus B is the idea. So this new vector is going to represent like the direct path instead of having to take two different steps there. So that's what we're going to look at for this case. So while hiking in the woods, Shelley walks 2 kilometers north, 30 degrees west from her camp, and then walks 2 kilometers directly east. How far and what quadrant bearing is Shelley from her camp? So the idea here is if I model this, first thing is north 30 degrees west, means that we're going from here. It's going like this, is 30 degrees is this spot right there. And she's going for 2 kilometers. Then she goes directly east for 2 kilometers. So she's going to go this direction for 2 kilometers as well. How far and what quadrant bearing is Shelley from her camp? So that means we're looking for this value right here. So we want the bearing as well as the distance there that was traveled. Okay. So what I'm trying to model here is that I have so this was 30 degrees here. I have a triangle now. I'm going to redraw that triangle over here a little bit. So I've got this, and I've got this right here. So what I have is 2 and 2 here. So what I need to know is this angle here, because then I'm going to be able to do law of cosines, because that's what we get from our scenario here. So I want to find this length, this distance. So if I find this angle here, what's helpful is knowing that this part is going to make 60 degrees because of north to west like that, meaning this, if it's going to directly east, that's parallel to the horizontal line. So this is also going to be 60 degrees here. So I got 60 here, and then I can model this x here using my law of cosines. So law of cosines is going to be x squared is equal to 2 squared plus 2 squared minus 2 times 2 times 2 times the cosine of 60. So when I go through that, I'm going to square root both sides here. So I plug that all in my calculator once, I get x is equal to 2. So that means this distance here is 2. So she's actually 2 kilometers away from that in that point. So then from there, we need to figure out the last angle. So I could do that one. So I'm going to find, well, I need to find this angle here. So one thing to notice is that because I have an x of 2, I actually have an equilateral triangle. So every angle is 60 degrees. So I come back here, I know this is 30 degrees here, meaning this little section also has to be 30 degrees. So that means that we can have the total thing. We want how far and what quadrant bearing. So if I look at it this way as a quadrant bearing, she's at 2 kilometers. And in this case, it's going to be north 30 degrees east at this in this scenario here. Okay, so and that's going to be it for today. So we're going to have some more practice with that one. So try to set this one up on your own. But that is it for 8.1 day 1 on our beginning of our vectors. Okay, so again, the biggest thing about this is looking at vectors as having both a scalar and a direction. And then also starting to talk about modeling our vectors as triangles when we do a resultant vector like this. All right, that's it for today. Take care, everyone. Oops.